Hi everyone. So in today's video, I am going to go over how pipeline parallelism is implemented in PyTorch. This is not going to be a coding video. I just want to learn myself how this is done, and I thought I could just record me studying this and post it so that if someone wants to study along, they can just watch this video. At a very high level, PiPPy was a package which PyTorch created for pipeline parallelism, but as the note suggests, it has now been moved to a sub package under this PyTorch API. And you also have like the documentation and a lot of examples in this current repository. So yeah, let's see how stuff goes. I'll just start here and then I have some links open that I'll consult. And yeah, I believe both of these are the same, so I'll just close one of them. All right, so YPP. One of the most important techniques for advancing SOTA in deep learning is scaling, and common techniques for scaling include data parallelism, tensor parallelism, and pipeline parallelism. So, in many cases, pipeline parallelism in particular can be effective for scaling. However, it is often difficult to implement, require intrusive code changes to model code, and difficult to implement runtime orchestration code. PP aims to provide a toolkit that does that. All right. So let's look at this. The PiPPy project consists of a compiler and a runtime stack for automated parallelism and scaling of PyTorch models. Let me also quickly open my notes so that I can take notes on the side. Ignore the paper notes name because I I'll just rename it later. Pipeline parallel PyTorch. Okay, so I just keep a few key points here. All right. Currently, PiPPy focuses on pipeline parallelism, a technique in which the code of the model is partitioned and multiple micro batches execute different parts of the model code concurrently. And there's also this article. Okay, this is the deep speed article. All right. So FPNU denote forward, backward, and wait update. So as you can see, you break your batch into these micro batches. For instance, you have 4 micro batches here. When and suppose your model is broken into 4 stages. So when micro batch 1 is in stage 0, nothing else is there, while when micro nothing else is there in other stages. While micro batch 1 comes to stage 0, you can send micro batch 0 to stage 1. Similarly, so by the time micro batch 4, which is index as 3, comes to stage 0, your first micro batch has already passed through. And then you can, once you've done like this for everything, you can then start your backward passes, and once backward passes completed for everything, then you can do your wait update. So as you can see, if you were to do one micro batch at a time, then you would first do this entire thing, then your second micro batch would start here, which would be quite inefficient. So instead of doing that, you basically break your batch into these micro batches and try to keep the different stages fed. So PiPPy does automatic splitting of the model code by tracing the model. Okay, so this is important. The goal is for the user to provide model code as is. And okay. Related to the last point, PiPPy supports non-trivial topologies including skip connection, tied weight layers. PiPPy provides configurable behavior for tied weights, allowing for transmission across pipeline stages or replication and gradient sync. All right. First class support for cross host pipeline parallelism, as this is where PP is typically used over slower interconnects. Yeah, so usually uh, you want your tensor parallelism, etc., which has more operations to happen over faster interconnects. And if you do not have, if you need to make the trade off, then pipeline parallelism needs to do less communication via nickel collectives. So you uh, typically then push this to be over the slower stuff. This is currently missing in the Torch GPipe based approach. Okay. I also plan to cover the GPipe paper at some point. Composability with other parallelism techniques, so you can also mix it with DP and TP. So you can get your famous 3D parallelism. Currently, pipelining and data parallelism can be composed. Other compositions will be available in the future. Okay. By the way, in Torch Titan, they do all this. So maybe they use some other version of pipeline parallelism. Support for scheduling. Okay, so you have fill drain with G-pipe, you have 1F, 1B, one forward, one backward, and then interleave 1F, 1B, and they also add more schedules. Okay, I'm also interested in looking at the architecture. So the setup code is okay. Examples, we'll look at the code. So let's look at how PiPPy works. PiPPy consists of a compiler and a runtime. The compiler takes a model code, splits it up, and transforms it into a pipe, which is a wrapper that describes the model at each pipeline stage and the data flow relationship. Okay, so the compiler does the splitting, and then at runtime, it executes the multiple stages in parallel, handling things like microbatch, scheduling, communication, gradient propagation. Okay, this is right. A good succinct summary. Now splitting a model with pipe, let's look at a quick code example. So this is your very simple linear array with an activation, and so this is one network block, and now your network is composed of several layers, as you can see. So you have several network blocks. So when you do your, and at the end you have this outward projection. So when you do your forward, you basically keep applying all the layers and then finally the output projection. So in this case, you construct your neural network. And this is like a fairly standard neural network. Now, this is free from Python code. Yes. Now let's see how do you use pp.pipe. So from pp you're importing pipeline, annotate split points and pipe. Okay, I believe Torch Titan also used some annotate split point thing. I pretty sure they're using the same API then, because there's no sense in having multiple APIs if they want a coherent ecosystem. Okay, why is this? Let me just zoom out a bit. Yeah, so this is your network. Then you make these imports, and you want annotate split points, which takes in mn. I believe that is your network. And then layer 0 is split point end, and layer 1 is split point end. Batch size is 32. How many layers are there? Is this mentioned somewhere? This is your dim layer dims, but where's the number of layers? Length of layer dims. Okay, so you have basically 3-layer neural network. So you're splitting once after layer 0 and once after layer 1. So once after this and once after this. Batch size 32. When you do your example input, you do chunks 4, then you can create a pipeline which takes the model, number of chunks, and the input. Now if you look at the pipe, you can see it's a graph module with pipe stage modules, and the split points are exactly as we were defining them. So once after layer 0, once after layer 1, and the rest becomes one stage. If I believe if you created one after layer 2, that would also become its own stage. So now your forward code, so all of this is automatically generated, so it automatically goes to these submodules. So first pipeline turns the model into a DAG by tracing the model. Then it groups together the operations and parameters into pipeline stages. Stages are represented as submodules where n is a natural number. Okay, submod n. They then use annotate split points to specify that the code should be split at the end of layer 0 and layer 1. So you get 3 stages. You also provide split point at beginning if the user wants to split before certain initiation point. Okay, so if you want, maybe you can then do before layer 1 and layer 2. That would also give the same result, I believe. While the annotate split point API gives user a way to specify the split points, you also have an API for in-model annotation, and this is the documentation for that. Okay, now using pipeline stage for pipeline execution, Given the above pipe object, we can use one of pipeline stage classes to execute a model in a pipeline fashion. So yeah, we're using torch run. Okay, rank and vault size. Rank is okay. The rank in OS variable and vault size. The vault size OS variable. You create a distributed group process. You initialize it, and then you create a pipeline stage, which basically takes your pipe. I believe pipe is this final thing, your pipeline. Pipeline state is a main pipeline runtime. It takes in a pipe object, the rank of this process and the device. We can now run the pipeline by passing input to the first pipeline stage. So if rank is 0, this means run the pipeline with input X, divide the batch into 4 micro batches, and then run them in parallel on the pipeline. Let me see. So you get this random input, which is of a particular batch size and input dimension. You put that on device. This is your input X. You divide the batch into 4 micro batches and run them in parallel on the pipeline. So if rank is 0, then you pass this to stage. Okay, this is your pipeline stage. If rank is the last thing, you take the output. Otherwise, you just run the stage. So for intermediate things, you basically do not need to pass the input. For the first GPU, you rank like the first rank is, I believe, the first process here. So for the first process, you need to pass the input. For the last process, you need to receive the output. And then for intermediate things, you can just run it. So you have 3 stages. We must run the script with 3 workers within torch run. So they basically run it on 3 workers. For this example, we will use torch run. We can collect up all of the code blocks above in a file name example.py and run it like this. Yeah. So this makes sense. And it's not like if you had 10, you would need different. If else, you only need these 3 conditions. So one to pass the input, one to handle the output, and one for everything in between. All right. So now I think I should also just keep a note of this. So all of these are from this file. I, so now if I consult any other source, I can also split them by source. Okay, so this makes sense. Uh, do we want to look at this pipeline parallelism thing? Not at the moment, maybe towards the end. How does this work? So this is, I believe, the architecture. Okay, what else do we have? This is an example. Okay, this is the test code. These are examples with say like Hugging Face and stuff. So you can do pipeline parallelism quite easily. This is okay. This is the port under the PyTorch package. So this is no longer called PiPPy now. And this is the documentation for the thing under torch.distributed.pipelining. Okay, let's maybe quickly look at this documentation first. Yeah, because this seems to be like these documentations are a bit more accessible. And then if you look at the architecture itself, like the architecture document, is easier to understand than, at least in my experience. Okay, Torch distributed pipelining is currently in alpha stage. API might change. It was migrated from PiPPy. All right. So pipeline parallelism is one of the primitive parallelism for deep learning. It allows execution of a model to be partitioned such that multiple micro batches can execute different parts concurrently. This can be good for large-scale training, bandwidth-limited clusters, and large model inference. The above scenarios share a commonality that the computation per device cannot hide the communication of conventional parallelism. For example, the weight all gather of FSTP. Hmm. What does this mean? I think what they're trying to say is that you cannot do enough computation communication overlap so that the communication is hidden. For instance, an all gather, if your GPUs have slow interconnect, then stall your hardware. All right. So what is torch or distributed pipelining? While promising for scaling, pipelining is often difficult to implement because it needs to partition the execution of a model. The partition of execution often requires intrusive code changes to the model. Yes. Another aspect comes from scheduling microbatches with data flow dependency. The pipelining package provides a toolkit that does these things automatically. So it has two parts, a splitting front end and a distributed runtime. All right. The splitting front end takes your code and splits it up into model partitions. The distributed runtime executes the pipeline stages on different devices in parallel, handling things like microbatch splitting, scheduling, communication, gradient propagation. All right. These this is pretty similar to what the PP docs had, but I just like keep things in hand if when I want to refer back in the future. Overall, pipelining provides the following features: splitting of model code based on simple specification. All of these schedulers, first class support for cross host pipeline parallelism. So if you have slower interconnect, maybe across nodes, if you don't have, say, InfiniBand, even if you have InfiniBand, it's much slower than communication within a, like it's slower than communication within one DGX machine. Composability with other PyTorch parallel techniques such as DDP, FSTP, or TP. The Torch Titan project demonstrates a 3D parallel. Okay, so the Torch Titan project does use this then. So build a pipeline stage. Before we run, we can use a pipeline schedule. We need to create pipeline stage objects that wrap the part of the model running in that stage. The pipeline stage is responsible for allocating communication buffers and creating send receive ops to communicate with its peers. So it needs to receive from the previous stage sent to the next stage. It manages intermediate buffers like for outputs of forward that have not been consumed yet, and provides a utility for running backward. A pipeline stage needs to know the input and output shape so that it can correctly allocate communication buffers. The shape must be static, so it cannot, okay, so it does not yet support different shapes at runtime. A class pipeline shape error will be raised if runtime shapes do not match the expected shape. When composing with a parallelism or applying mixed precision, these techniques must take into account so the pipeline stage knows the correct shape and D type. Okay, so this is important. It, I believe this is uh, to make sure you can pre-allocate space, but I don't think this should be a super big blocker. Like I think if they wanted to, they could support dynamic shapes and dynamic D types. Users may construct a pipeline stage instance directly by passing in an nn module. This may require changes to the original model code. See example option 1. Okay, we'll see that later. Alternatively, the splitting frontend can use graph partitioning to split it. The technique requires that the model is traceable with torch.export. Okay, so this is important. If auto splitting, then requirement that the model is traceable with torch.export. Composability of the resulting NN module with other parallelism techniques is experimental and may require some workarounds. Usage of this front end may be more appealing if the user cannot change the model code. So they have code for that. We'll see that as well. So once you have the pipeline stage, you need to build a schedule. So if you're using a gpipe schedule, you import that, you create a schedule with the stage and the number of micro batches. You take the input data, and then if in rank is 0, you start with input x. You like run for the input, and for other ranks you just keep passing the output, like run the next step and saving the output. And as we was looking at in the PiPPy code, you could also have like a separate L elif where rank is not the final rank. There you could not save the output and just run this, and for the final rank you can take the output. So in this case, they only have two nodes, so it doesn't make sense to have three. If else, but like if it was 10, then you could probably save some space. Now, options for splitting a model, you could do manual split. To construct a pipeline stage, the user is responsible for providing a nn.module instance that owns the relevant nn parameters and nn buffers and defines a forward method that executes the operation relevant for that stage. For example, the condensed version of the transformer class defined in Torch Titan shows a pattern of this. Let's see. So this is a transformer. You have your embedding, then using a module dict lets us delete layers without affecting names, ensuring checkpoints will correctly save and load. Okay, so they have this module dict, and for number of layers, you basically create layers as transformer blocks, and then you have output. Now during forward, handling layers being none at runtime enables easy pipeline splitting. So you first do embedding. If it exists, else it assumes that it has already been converted into tokens. Now you keep uh, doing your pass through the layer, and I believe this is your frequencies for the positional embeddings. And finally, you apply the norm and you take the output and return it. So handling layers being none at runtime enables easy pipeline splitting. I don't know why this is the case, but I believe it say might just be the code doesn't like the backend code then doesn't need to think about all of those extra conditions. So a model defined in this manner can be easily configured per stage by first initializing the whole model using meta device, deleting undesired layers for that stage, and then creating a pipeline stage that wraps the model. Oh, okay, now that makes sense. So when you do this meta initialization, you're basically not initializing the weights, you're initializing you first can like load up the model in some form, split it. Once it reaches, like for instance, if the model is too big to fit in one GPU, then how do you initialize it? So you can still initialize it on one GPU using this meta device. Sorry, on using this meta device. So it doesn't really need to fully materialize all its parameters. Then you can split it, and then you can materialize it on the different GPUs. So you only have a two-stage example. So first you construct the model, then delete the parts that do not need for this stage. In practice, this can be done using a helper function that automatically divides the layers. So if you are on layer 0, you can delete layer 1. If you are in layer 1, you can delete the token embedding in layer 0. For layer 1, you need the norm and output. So you don't delete that as you do that for stage 0. And then you can construct your pipeline stage. The pipeline stage requires an example argument input args representing the runtime to the stage, which would be one microbatch worth of data. The argument is passed to the forward method of the stage module to determine the input and output shapes for communication. When composing with other data or model parallel techniques, output args may also be required if the output shared D type of the model chunk will be affected. Okay, now how do you split it automatically? This is your model now, and you can see that it has okay an embedding, then you have two layers, and then you have this LM head, language modeling head, which I believe is basically your linear projection into the vocabulary space. So that output projection matrix. Now this is your input. You're splitting it at layer one's beginning, which basically means that you're splitting it after layer zero, and the second stage is everything after layer one. So now you can look at your graph module and you can see your submodule 0 is embedding in layer 0, and your submodule 1 is layer 1 and the LM projection head. The model partitions are represented by submodule submod 0 and submod 1, each of which is constructed with original model operations, weights, and hierarchies. In addition, a root level forward function is reconstructed to capture data flow between the partitions. Such data flow will be replayed by the pipeline runtime later. So this is basically uh, the pipe object provides a method for retrieving the model partition. So you can get the part for a certain stage index, and that is an nn dot module. And you can also create an optimizer, save or load that particular thing, and apply further parallelisms on top of that. Right. Pipe also allows you to create a distributed stage runtime on a device given a process group. So this just creates a stage. Alternatively, if you would like to build the stage runtime later after some modifications, you can use a functional version. So this first, okay, so you first take stage mod, and instead of directly building the stage, you first also apply DDP on top of it, and then you build the stage. The pipeline front end uses a tracer to capture the model. If your model is not fully graphable, you can then use the manual front end below. The manual front end is uh, okay. You have examples for Llama and GPT-2. Let's just look at Llama then. So you're importing auto model and auto tokenizer from transformers. You're creating your model. Then you're also creating your tokenizer, and you have two samples in your batch. Rank and volt size are basically telling you what's the rank of this particular process and what's the volt size. So I believe volt size is 2 in this example, and rank is then 0 or 1. You can also have bigger volt size. So basically, if you have 8 processes, you have a volt size of 8. Yeah, number of micro batches is, let me see. So what is this MB prompt? This is the prompt for the micro batches, and then this is the full batch prompt. This is the input at runtime. You're splitting it after every layer. So basically, you're doing it at the start of every layer, so you get as many splits as the number of layers, excluding like the input and output thing. So the embedding part will probably be a separate, yeah, the embedding part will be a separate thing, and then the output projection will be a part of the last layer. Your number of micro batches is 4. You create a schedule, and then you can then just run this. So looks good. Now, how does this actually work? They create a DAG, as we saw. Then it groups together operations and parameters needed by a stage into a reconstructed submodule. Different from the conventional submodule access methods like module.children, the pipeline API does not cut the model structure but also uses the forward function of your model. This is necessary because model structure like module.children merely captures information during init and does not capture information about forward. Said differently, module.children lacks information about the following aspects key to pipelining. I think there's a typo here. Yeah. Execution order of child modules and forward. You can find the children, but you don't know what's the order for them, what's the activation flow, and whether there are functional operators between child modules like relu or add. Mhm. The pipeline API on the this is because if you have basically this part defined in your forward and not in your mod children modules, then since it does not capture the forward, it cannot figure that out. The pipeline API, on the contrary, makes sure that the forward behavior is truly preserved. It also captures the activation flow between partitions. Another flexibility is that split points can be arbitrary. In the split partition, the original model hierarchy related to that partition will be reconstructed at no cost to you. At a result, fully qualified names pointing to a submodule or parameter would still be valid, and services that rely on FQNs like FSDP, TP, or checkpointing can still be run. Implementing your own schedule, so you can also create a schedule with extending these classes. Let's see. So this single schedule is for schedules that assign only one stage per rank, so only one stage per GPU. Multi is where you can have multiple stages per rank. Like GPipe and 1F1B are single schedule, whereas interleaved one forward, one backwards, loop BFS, interleaved zero bubble are subclasses of pipeline schedule multi. You can also run the logging. This is the code, the micro like the documentation for the code. I'm not going to go over that. I do want to look at all the schedules. So gpipe schedule, so all micro batches in a fill drain manner, 1F1B, one forward and one backward on the micro batches in a steady state. The interleave 1F1B, so it's from this paper, will perform one forward and one backward in steady state and support multi stages per rank. So you can have multiple stages per GPU. When micro batches are ready for multiple local stages, interleave 1F1B prioritizes the earlier micro batch. The schedule is mostly similar to the original paper. It differs by being relaxing the requirements of number of micro batches should be exactly divisible by the number of pipeline stages. All right. Then you have loop BFS pipeline. Similar to interleave 1F1B, loop BFS supports multiple stages per rank. What is different is that when micro batches are ready for multiple local stages, loop BFS will prioritize earlier stages running all micro batches at once. In zero bubble is, I believe this paper was quite trending recently, will perform one forward and one backward, and for the micro batches in steady state and support multi-rank per stage, uses backward for weights to fill in the pipeline. This is implementation of the zero bubble thing. Oh no. Uh, does it actually have zero bubble delay? I don't think that's possible. But I believe there's a paper recently which has that. And these are like subclasses. All right. So this was good. Okay. What next? Hmm. Yeah. I'll now look at the architecture. So program capture and intermediate representation. ir.py defines the pipe class, which is the main intermediate representation as we were looking at in the examples. This intermediate representation consists of restricted fx.graph module. In the top level fx.graph representation, the IR is limited to only the following node types. We have placeholder and output nodes to specify overall pipeline input output, call module nodes to represent calls into pipeline stages, call function with a target of operator.getItem, for unpacking tuples, call function with a target of ir.stage backward for the purpose of modeling the backward computation, and call function with a target of torch.add emitted solely for accumulating gradients that have multiple uses in backward pass. Okay. The top level effects.graphs gives us a topological ordering, data dependencies. This is more general than existing pipeline APIs because it supports arbitrary non-local connections like skip connections. So you might have skip connections which have starting in one stage and ending in another stage. You can create IR from existing PyTorch modules using one of the several frontends. Expose a static methods on pipe.pipe.from sequential, takes an argument an instance of nn sequential and returns a pipe instance. So this is like a list. You also basically, I believe this is a skip connection, mods plus equal mods 0, or you basically have the last first layer at the end again. Then you have this, you create the sequential object, you create this pipe, and you basically get uh, every linear layer as one submodule. During forward, you take the input, then you perform uh, the forward through each of the layers one by one. Similarly, we can use pipeline to use torch effects, tracing an arbitrary NN module. This is an arbitrary module. You can, okay, so you can place pipe split at these places in the forward pass. Hmm. So does it automatically do this? So this should be then one stage, and another stage. And it seems that this is the case. And in the forward, it handles that. The pipe dot split to explicitly demarcate within the code when we want pipeline boundaries to be from where we want them to be from. Tracing will collect all data dependencies and emit corresponding dependencies to the pipeline graph. ir.pipe split wrapper and ir.annotate split points can be used to unintrusively specify split points. So you can do that like we saw in the code after the model instantiation. Skip connection value in the original program from tracing will correctly detect the usage from stage 0 to 2. Notice that self.mm param is used both in pipeline stage 0 and stage 1. Since we have specified multi-use parameter config.transmit, I suspect this system will emit code that will keep this resident in stage 0 and transmit the value for use within stage 1. This can also be modified as a dictionary mapping names to value one of transmit or replicate, or it can be left as none to specify the default behavior transmit. Multi-use parameters can also be replicated. That is, each stage pipeline that uses a replicated parameter will have its own copy of the parameter, and the system will record information about this replication such that the runtime can insert the proper synchronization operations upon update. Let us see run the above example and you get this. So you have parameters, submod 1 and parameter. The pipe instance has an attribute replicated params, which is a record of all parameters that are replicated across stages. This, ob- this object is a dictionary list of dictionaries. Each dictionary represents a single value that has been replicated across stages. The key of the dictionary are the stage names, and the values are name of the parameter itself. Note that not only do we see parameter in the above example, but we also see the parameter replication. Self.lane is a leaf module in torch.fx parlance, and since we cannot see into the implementation of a leaf module, we automatically replicate leaf module parameters. Note that we could hypothetically emit code to fetch the parameter values from leaf modules and transmit them to usites, but that will require further development. All right. Hmm. I don't think I have like enough understanding of the PyTorch FX stuff to understand the program capture part, but I'll just quickly look at what other things are relevant here for me at least. Is the scheduler nodes. Hmm. So in this case, you're starting to do backward once it ends, right? A note about the correctness testing. Uh, Not guaranteed to be bitwise equivalent. A proposed way to get around this when testing is to run the full batch and slice out the results from the full batch that correspond to each micro batch, and then cat those partial results together. This is demonstrated when use whole batch is true. And this is other considerations for the API. All right. I think this was all I wanted to do. I now understand how the PiPPy thing works, how it's also implemented within the Torch or distributed pipeline ecosystem. I just will quickly look at some more examples. Let's see. PiPPy and GPT-2. So you're basically loading GPT-2 for classification. Where is the run command? So you're running for 4 processes. Okay. You've generated a schedule and the inputs. For rank 0, you pass the input. For others, you just keep taking the out and then you destroy this. I am curious about how stuff will change if you also have another else condition. They have the world sizes in Arc, right? I think or hope they do. Let's see. Yeah, they have world sizes in Arc. Hmm. All right. Yeah, I think this will be fairly similar for all this. So yeah, I think I'll end this video here. If you like this content where I just brainstorm and learn new things, feel free to drop suggestions for what else should I cover. But yeah, this is a high level overview and some discussion on how PiPPy and pipeline parallelism works. Thank you.